search method of AutoML. In this, we are going to discuss about customizing a Bayesian optimization search method. This is a practical guide about Bayesian hyperparameter optimization with Optima. This is one example we have taken. And this is achieved by training a performant and machine learning model involves tuning two types of variables, parameters and hyperparameters. Parameters are the model's internal variables like weights in a neural network or coefficients in linear regressions. Parameter can be model's internal variables, weights, neural networks, coefficients, or bias or example that are learned directly from the training data set. And hyperparameters are the external configuration settings like learning rate or the number of trees in a random forest. Also, the epochs or number of epochs you want to do it, and iterations. That are the hyperparameters that controls the training process itself. These are not learned from data. Must be set before training begins. It is a prerequisite before starting the training. You have to set the hyperparameters. Hyperparameter optimization is the critical process of finding the optimal combination of these hyperparameters. So you have to choose the right parameter like epochs, and learning rate to obtain the optimal result. It should not result in underfitting or overfitting and kind of situation at the end of the result, at the end of the process. You need to optimize these hyperparameters, and this is a critical process of finding the optimal combination of these hyperparameters to maximize your model's performance on a data or any data or unseen data. And challenges with the basic tuning methods like grid search and random search. Those are the basic issues or challenges you have in basic tuning methods. Grid search exhaustively tries every combination of hyperparameters in a predefined sets, and while 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 thorough it becomes computationally infeasible as the number of hyperparameters grows. What happens is like the problem known as a curse of a dimensionality happens. The number of hyperparameters keeps growing, these kind of issues will happen. The grid search exhaustive things, and random search randomly selects a fixed number of hyperparameters combinations to try. Like it is often more efficient than the grid search because we have a random search and fixed number of hyperparameters in this scenario. Grid search, but can still be wasteful as it may evaluate many poor combinations and completely miss promising regions of the search space. And the fundamental limitations of both methods is that they treat each hyperparameter evaluations as an independent event, ignoring everything learned from the previous trials and trainings. And also for complex models and large data sets where each training is run is expensive. This inefficiency becomes a major bottleneck in that kind of situations. And next is a smarter approach, Bayesian optimization. Bayesian optimization offers more intelligent, efficient alternatives. It is a sequential design strategy that uses the results from the past evaluations to inform the next set of hyperparameters to test. It's over the period of time, it gets perfect because it takes the learning from the old or previously trained previous trainings and learnings, and it pass on to the next set of hyperparameters to test. Instead of searching blindly, it builds probabilistic models, a surrogate of the objective function, and uses it to predict which hyperparameters are most likely to yield better performance or a best performance. This approach allows it to focus computational resources on exploring promising regions of hyperparameter space, dramatically reducing the number of iterations needed to find a near optimal configurations. The key components of Bayesian optimization are search space, objective functions, surrogate model, acquisition functions. So these are the four key components of Bayesian optimization. Uh, so a search space, the defined range of possible values for each hyperparameters, example, learning rate from 0.00001 to zero point 0.1. A well-chosen search space is crucial for success. And next is a objective function, a function that takes a set of hyperparameters, trains a model, and returns a performance metric, example accuracy, FN score, that we wish to maximize or minimize. This function is computationally expensive to evaluate. The surrogate model is the next one. The surrogate, a probability-based model that approximates the true expensive objective functions. After each evaluation, the surrogate is updated to incorporate the new result and refining its understanding of the hyperparameter landscape. So it takes from the old result and it upgrades and incorporates with the new result so that it can refining its understanding of the hyperparameter landscape. So it will be a better performance. And common choices are Gaussian process and tree structured Parson estimators, TPE, and acquisition functions, a criterion that uses a surrogate model to decide the next most promising hyperparameters to evaluate. It strategically balances explorations and exploitations, testing near known good results, and explorations testing in uncertain regions. Those kind of things happens here. Examples include expected improvement and probability of improvements. So these are the four key components of Bayesian optimization and Bayesian optimization loop. So update the surrogate model based on all previous trials, find the hyperparameters that maximize the acquisition function, then evaluate the objective function with these new hyperparameters, add the new result to the history of trials, repeat until a stopping condition is met, example, a match number of trials or no significant improvements. Introducing Optina, a framework of automated tuning, and so you can see the training data set is taken and it is fed to the model training and training with CL model that is and optimize the objective functions, and then it again goes to the validation data and it is fed to the model. So from the model training, it goes to the training model, and from there it happens goes to the evaluation on validation uh, data. From the model training, it moves on to the next final model. So after the training, it goes on to the next model to make predictions, alter n trials. So after n number of trials, you would result the final model, trained model, and save trials results in Optune. That is, save tuning results to Neptune. Then it goes to the evaluation on the validation data. So Optino is a powerful open source hyperparameter optimization framework that automates the Bayesian optimization process. It is designed to be lightweight, modular, and framework agnostic, working seamlessly with PyTorch, TensorFlow, Scikit-learn, and others. Its key advantages includes ease of use, state-of-the-art algorithms, parallelization, visualization. So ease of use is define a search space and an objective function with intuitive syntax. State-of-the-art algorithms efficiently implements algorithms like TPE out of the box. Parallelization supports distributed optimization across multiple cores or machines. Visualization is offer tools to analyze and visualize the optimization. Hands-on example of tuning random forest with Optina. So you can see here tuning a random forest classifier on the classic iris dataset. So step one is to install dependencies, bars, and install PAP, Optina, Scikit-learn libraries. And next is the package. And next is step two, prepare the data and define the objective functions. We add some noise to the iris dataset to make the problem more challenging and tuning effect more noticeable. So this is a sample code for the same. And step three is create and run the study. The study object orchestrates the optimization. We direct it to maximize our objective function and use the TPE samplers. So next is to create a study with the TPE samplers and maximize the objective score. Then the output, the best result. Then it goes to the output, the best results, best trial. Okay. Running this code will perform 15 intelligent trials with each new set of hyperparameters being informed by the result of the last. So you can see here the 50 trials happens. Um, at the end of each trial, the next hyperparameter set will know what kind of new set of hyperparameters being informed by the result of the last, so that you will get the improvised version of the improvised results. And next is step four was optional. Track your experiments with Neptune. You can either track it, or you can first you have to install the Neptune package onto your notebook. And these are the steps to import the Neptune and create Neptune callback for optional. So this one you can just for study purpose you can skip this purpose. It's not mandatory. And best practices for effective optimization start with informed ranges, and next is don't define your search blindly. So do not define your search blindly. Use domain knowledge, research papers, or prior experiments to set reasonable bounds for your hyperparameter. So always have a domain knowledge, or what's the purpose of your exercise or experiment, and based on that you have to do the fine tuning. And next is choose the right metric. So in this, choose the right metric. Ensure your objective functions return yeah, returns a metric that accurately reflects your project goals. Next is don't skip on trials. While Bayesian optimization is efficient, it is still needs a sufficient number of trials to cover to coverage. Start with moderate number, example 50 to 100 example, and increase if necessary. And the next one is last one is validate your findings. So it is always to analyze what you have found, and you can bring in information, sorry, improvisation on the next trials or next so that is validate your findings. What is always validate the best found configuration on a held out test set to ensure it generalizes and it's overfit to the validation process. Next is like conclusion. What is the conclusion of this Bayesian hyperparameter optimization? Implemented through powerful tools like Optino represents a significant leap over traditional methods like grid and random search, and by leveraging past evaluations to make informed decisions about what to try next. So each trial, like if 550 or 100 trials, the hyperparameter optimization happens so you will get the learning from the previous hyperparameter optimization trial one, and when you go to the trial two, you will have the better information what needs to be tried or what needs to be optimized. Accordingly, you will choose the hyperparameter values. By leveraging past evaluations to make informed decisions about the what to try next, and it finds a superior model configurations in a fraction of time. And adopting this method is a key step towards building more accurate models efficiently, and is a cornerstone of modern machine learning workflows. Thank you all.